So the big topic for tonight is electric potential. And it's kind of related to potential energy. In fact, we could call it electric potential energy, but then if you've noticed, we've done sort of an interesting thing when we talked about fields, is that instead of talking about forces on charges, we instead took a look at how space was mapped out. So that if you put a charge anywhere in space, what kind of force would it be? And that will be the same spirit that we do with electric potential. So just to clarify, we're going to split up this idea about potential energy and electric potential, but also pull on some ideas from Physics 1, where we slogged through force vectors and a bunch of other stuff until we got to energy, and then suddenly things were a lot easier. So we're going to touch on all these topics, but the last three will be on Thursday. So let's take a look at this for a second. So let's imagine that we have long chains of charge next to each other. And one of the things that we know is that when you have conductors and you apply charge to them, what will happen is that the conductors will spread out because they repel each other. And they'll spread out as they repel each other so that they maximize the distance between each other. So if you take a look at the left side of this conducting plate, we have the charges all spread out evenly. If it was an insulator, it's possible to have the charges more clustered. But one of the things that we know for sure is that when you apply charge to a conductor, it all just spreads out. And if we apply an equal charge over here, then we see the electric field lines between the two plates are nice and straight. We call that a uniform electric field. Now, one of the things that's true about potential energy is that if we allow the system to do work, then what it's going to do is access the potential energy that's stored in the system. And in this case, what is happening if we had a positive charge here next to this positive conducting plate, and we allow it to just let it run away. It's being repelled by these positive charges and being attracted by these negative charges. And so it'll run from a high potential energy to a low potential energy. And that's what the electric field is doing. It's accessing that potential energy. And when it's all done, we will see a loss in potential energy. Now, if this charge is just allowed to run free, then it will gain speed and it'll gain kinetic energy. And that's a similar theme that we saw in Physics 1, where you let a rock roll down a hill and the potential energy becomes kinetic. So it's the electric field accelerating this charge, and it's doing work. So back in the day when we were doing Physics 1, we recognized work as being force times distance. But if the field is doing the work and it's taking potential energy away, then that's going to be a negative number. So in terms of the potential energy, that energy is not going to be accessible anymore. It's gone. It's been turned into kinetic energy. So this is the loss of potential energy is related to the work done. So we define this new thing as an electric potential, which is the potential energy per unit charge. And that's a volt. So as we mentioned before, when we were working in the lab, we had charge carriers, and those carriers carried energy. And we said the energy per unit charge are volts. So yes, you can do joules per coulomb. There's also another way to write this unit. So the potential in going from B to A, and so that's a potential difference, if you will. The difference in electric potential between point A and point B is equal to the opposite of the work done per unit charge. So if I multiply both sides by Q, then I would have the relationship between work and the change in potential energy. So I'm going to stop for just a second, and I'm going to get out of this presentation mode. And then I'd like to share a little file. Actually, I was working on this right before we started to, right before I got online. So you can see this on Moodle. This is a file called Hiking the Electric Potential Wilderness. Now, if you had a chance to do that electric field activity, which by the way, you can just submit to me with as a PDF, then you had a chance to map equipotentials. I'm going to zoom away from this just a little bit. And so what this represents is I've got a positive charge here and a negative charge. And these green lines represent lines that all have the same potential energy. It was hard with the mouse to get nice round values for these lines of equipotential, but at least they're labeled. So all the points on this line, which it looks almost circular, are going to have a potential energy of 13 volts. And then this line, 8.3 and 4.6 and so on. Now, you're probably familiar with what a topographic map is. A topographic map is similar. So it plots out lines of equal elevation. Let's just grab one from the internet really quick. Sure. So this is showing sort of the layout, but let's get a more generic one. And let's go to images. Okay, so here's a good example. This shows lines of equal elevation. And one of the things that we know is, let's see, let's pick one that. I can just stick with this one. So when the lines of equal elevation are really close to each other, then that means this region is pretty steep if we were to hike it. Now also where they're close together and they're sort of notched like this, that's the direction that water would flow if it was given the chance. And the same thing is true with equipotential surfaces and charge flow. So what I did was I said, all right, what if we could bisect this? If this is sort of like a contour map or a topographic map, what if I was to just hike along a line like this? Now, in Explorer terms, hiking along a straight line and exploring the terrain along a straight line is called a transect. So what would it look like if we did a transect from this? We start over here and we just walk. If you did that, then this positive charge sort of represents a hill or a mountaintop. And then the minus charge represents a hole in the ground. So I've actually done this, and I went through and I plotted the values, and I got a graph that looks like this. So if you were to come and start walking along this transect, it would get steeper and steeper. And the steepness corresponds to the electric field. And so this would be hard for me to walk uphill. I would be doing work against gravity, and I would be storing potential energy. Then after this shoulder, now I'm walking downhill and I'm losing gravitational potential energy because really gravity's doing the work. And it continues to do its work all the way down into the bottom of this hole. And then to climb out of it, I'm going to have to do my own energy. I'm going to have to exert my own energy to climb my way out of it. So that's what we mean by, I'll just write the equation right here. Work is equal to minus Q times V. So if we wanted to find out how much work is required, then all we have to do is take a look at, let's suppose we're walking from here up to here. all we have to do is find out the difference in elevation and then multiply it by Q, and then that's how much work we'll need to do. Now, if we do work, it stores energy. But if you let the charge run downhill, then it takes potential energy away. All right, let's go back and take a look at our notes and see if we can make a little more sense out of that. My notes are stuck under here.
Can I ask a question about this?
Yeah.
So once you go to, so you're in the negative energy, you're at the lowest point, and then it's moving back towards zero. Is that it trying to like find equilibrium? I don't know.
Yeah, well, so that's a good question. And what does the negative energy state mean? So this is electric potential, which is energy per charge. And if you want to actually get an energy value, you just multiply it by how much charge you're talking about. So an interesting thing that happens is that, like, let's suppose we took our pet charge out for a walk and we got our pet charge up to the top of the hill, but somehow they went off leash. Well, our charge is going to naturally just run downhill and get down in here. So this is a negative energy state. And in order to get free again, it's going to cost you energy. So if you were hiking this and you found yourself kind of stranded down here, then you're going to have to exert some energy in order to get out of this hole. How much energy? Well, this energy right here. This is a voltage right now, but if I just multiply this difference in voltage times the charge, then I do get energy. These energy diagrams are really important because they essentially identify the difference between free states and bound states. So if I have a charge that's down here and it doesn't have enough energy to get out, then we would say it's in a bound state. And it's going to take energy to liberate it. But if I've got a charge up here, it's in a free state and it's free to roam wherever it wants to. Maybe it rolls back down, or maybe it rolls down here and puts the brakes on and realizes, no, I don't want to go down that hole. So anyway, that's the relationship between work and potential energy, and therefore electric potential, because electric potential is just potential energy per charge. Okay, well, let's take a look at a couple of practice problems. And I kind of lost my notes here, so let's just see. Okay, we'll be in here. This is, I believe, a Google Drive. Right, so I don't know what happened to that slide deck, but I'll just pop it open really quick. Okay, and I'm going to stay away from presentation mode, so it's a little bit easier. Okay. So this is another analogy. It's kind of another diagram. I'm thinking about what we've got. So you would recognize that if I lifted two rocks up to the top of a cliff, that it's going to take some work. And the work done is equal to the potential energy that gets gained. That's work that we do. So if we're trying to get the rocks uphill, it costs us energy. So then the work we do equals its gain in potential energy. However, there's something about being on top of that rock, because we know that when the things fall, potential energy is going to become kinetic, and they'll actually have the same speed when they hit the ground. But that's weird, right? So they don't have the same potential energy. And then they won't have the same kinetic energy when they hit the ground, but it looks like that there's something that will be the same about them. And so the idea is we could call this potential energy per kilogram. And that would be a lot like voltage. So we establish a potential energy difference, but then allow charges to flow as they might. Okay, good. Let's go forward. So we can rewrite this in a couple of different ways. You'll recognize that Q times E is the electric force. So this is one way we can, in fact, figure out work. And then the other way, of course, is to look at the electric potential. Right, and so the electric field actually winds up being the slope of that graph that we saw before. Right, the negative of that slope. Okay, oops. All right, I think we can move forward and then take a look at some practice problems. So why don't you take a look at these with me? I'm going to zoom in a little bit. Okay, I'm going to stop sharing my screen and we'll go take a look at the notes for today. And one more time. I still have to zoom in on the whiteboard, but my daughter's put some flowers out here for you just so you can see that. All right, let's go to a different screen. Take a look at the whiteboard screen. Yeah, there we go. Okay, I have a work light here. I'm going to turn that off. That'll cut down the glare a little bit. Okay, and I'm going to shut this other screen off. Yeah. So that looks a little bit better. And let's zoom in just a little bit more. Yeah, they left a little note for you, so. Okay. We're going to start off by taking a look at a pretty straightforward example. And if you're looking at the agenda with me, you can get down some of the specifics. But it's talking about work done by the electric field. And we're moving a proton from a point with a potential of plus 125 to negative 55 volts. And it says express your answer in both joules and electron volts.
Sorry, which question?
I'm looking at number 2.
Okay, thank you.
Yeah, sure. Okay, let's do this. Let's flip this over. Yeah. Cool. Okay, so we have some kind of region and we start off. And if I use the gravitational analogy, we've got a peak up here, and then the height of that peak is 125 volts. And then I take a positive charge, because it says a proton, and moving to a point where the potential is negative 55. So just to kind of build on that idea that I graphed before. So this is negative 55 volts. So the work done by the electric field, and I'm just going to categorize this a little bit. So this is not work that we do. Because if we push the proton up the hill, it would take work from us. It would cost us energy. But then when we get it up here, it's going to be stored energy, and then it would be potential. So then it would be a gain of energy. So here's my positive charge up here. I'm just going to switch to my camera so I can see how well that shows up. All right, that's looking okay. And then, so the electric field is going to take it downhill, and then my potential is going to be here. Now, the Q that we're talking about is a proton. And a proton has a charge that's equal to 1.6 times 10 to the minus 19 coulombs. And so work done is equal to minus QV. And actually, I'm going to write this as delta V because that's a little bit more obvious. I don't like it when the delta V's are done with subscript letters because it can be confusing about which way you're going. So delta, we always do final minus initial. So this is going to be minus. And we'll put the Q in just a second because there's something I want to show. And then the delta V is we put in where we wound up. Always do final minus initial. So final minus initial. And the final place I wound up was negative 55 minus the initial I started off with, which was 125. Right, so we can combine those. That's going to be negative 180. And we subtract those two. And so the work done is going to be a positive number. And that's because if we just let this thing roll downhill, it would gain kinetic energy. So then, yeah, the work done by the electric field is positive because it's giving energy to that particle, but the particle is losing potential energy. So that's a cost. And of course, what it gains plus what it lost is equal to 0. That's energy conservation. So we'll follow up on that in just a second. So let's subtract these two, and that gives me negative 180. So this is going to be Q times 180 volts. So there are actually two different ways of writing this. So let's do this in joules. To get joules, what I'm going to do is take the charge, which is 1.6 times 10 to the minus 19, and multiply by 180. Right, so that's not too bad. And that's going to give me a total of 2.88 times 10 to the negative 17 joules. But there's this new unit called an electron volt, and there's a slide on this too, so I'm kind of jumping the gun a little bit, but I think that's okay. This unit is called an electron volt, and I mentioned before when we were talking about energy units that a A joule is actually a very small unit of energy. So if you were measuring your own personal electrical energy usage, a joule would be too small. You probably want to use kilowatt hours. But if we were talking about a proton, then a joule is way too big of a unit for energy. So we have a quick workaround. And I wouldn't worry about writing this down yourself, but let's suppose you're going out shopping for a car and the car has, I don't know, 105K miles. So what we know is that that K stands for 1,000. And so if it's not in kilomiles, which is essentially what that's saying, it would be 105,000 miles. Now I know that's super obvious, but I just wanted to use that to set up. What electron volts mean is that an electron volt is the amount of energy that an electron gains when it's accelerated through a potential difference of 1 volt. So the E actually takes up the 1.6 times 10 to the minus 19. So the answer actually is just equal to 180 electron volts. So that's a really cool shortcut. Since we have V in voltage, and we're multiplying by the elemental charge, which is 1.6 times 10 to the minus 19, we can just replace this with the letter E. And that's letting us know that this is a good unit for energy if we're talking about fundamental charges. So if we want to get joules, we can just multiply it by the fundamental charge, and there you go. So here's our answer. Now, before we move off on this, I know this is super abstract, but I do want to kind of ground you in some physics 1 concepts, because when we did conservation of energy, that seemed to be, people like that a lot. So let's just take a look. So far, what we've talked about is that the work done by the E field is equal to minus the change in potential energy. But if this particle is free to move, what happens with the work done by the electric field is that it's equal to the positive gain in kinetic energy, if it's in fact accelerating this particle. Right? So if we add the two together, then that's 0. And this concept is called conservation of energy. I think you also, just to make another connection, you remember when we did the first law of thermodynamics, and in our total internal energy, the work had a minus sign in front of it? It's for exactly the same reason. If the electric field is doing work, then that means it's throwing energy out into the rest of the universe, and we're not storing it anymore. So I guess that makes work sort of like an anti-hoarder, I'm trying to hoard potential energy, and the work's like, get rid of it. I don't know if that analogy really works. All right, just checking in with you. Questions really quick. That was a lot for just a level 1, number 2 problem. Okay, so we're going to do a couple of these. I want to do about 5 altogether. Let's see. So for 6, we got an electric field, and we want to set up this electric field between 2 parallel plates that are 11 millimeters apart. How big a voltage do you need? Let's see what's this one. There we go. All right. Awesome. Let's throw some numbers up here. So in 2 parallel plates. Hey, look, I've got charges here. Let's throw those on there. So I think this is 6, right? So we have 2 parallel plates. So we've got some positive charges. Oh, visual aids, my gosh. And the electric field between these plates is going to be uniform. So this is positive. And then this is negative. So our electric field lines, you know, if you were trying to do the geographical equivalent of this, this might be a straight ridge on a mountain range, and then this might be a canyon. And then our electric force vectors, or electric field vectors rather, are going to be straight in between them. So this is high PE, and this is low PE. So the slope between these two, if we were trying to imagine this as a you know, the difference between a mountain range and a canyon, the slope corresponds to the electric field. It actually corresponds to the opposite of the electric field. So running downhill, V is equal to minus QE. Actually, let's think about like this. Work equals minus force times distance, or minus PE, we'll do it like that. But potential energy is charge times electric potential, which is delta V, voltage, right? Energy is in joules, voltage is in energy per charge, right? So we can break that up. Now the work itself is going to be equal to a force times a distance. And then if we remember the electric force, well, that's going to be Q times E times D. And now we can see the relationship between electric potential and the electric field itself. So the Q's cancel out. And if we divide both sides by D, then I don't think blue shows up very well. Sorry, change gears here. So if we divide both sides by D, then it turns out that the electric field is equal to minus delta V over D. From this definition of electric field would have units of newtons per coulomb, but from this definition, they would have units of volts per meter. All right, so that's where things show up from. In this particular example, we have a value for D. The distance between the plates is 11 millimeters, and then our electric field that we're looking for is 640 volts per meter. So 640 volts per meter is what we're looking for. So we're going to have to charge up this plate, and the easiest way for us to measure how much it's charged is by putting a voltmeter across it. Again, this is 11 millimeters. And now we're ready to throw things in there. So the potential difference, the actual order doesn't really mean very much. So let's do 640 is equal to, but we need SI units. So instead of 11 millimeters, I'm going to go point delta V over the minus sign, and the distance is 0.011 meters. So we multiply that out, and then we have the voltage difference. And just like we saw when we met in person last week, that the order doesn't really matter. So we can get a negative number for this, but it doesn't really matter because if you're measuring this, then you just flip the leads on your voltmeter and you get the number. So the challenge really for this is that we have lots of new vocabulary. Your head's probably still spinning from all that work that we did last week with circuits. And now we're sort of like looking on the inside about what's happening. But really what we're doing is we're saying, since charge itself is kind of amorphous, we don't, the concept of having individual charges, well, the charge is 10 to the minus 16, and those numbers are just incomprehensible. So instead, what we usually talk about is the same thing we would do with fluids. Instead of talking about force, we would talk about pressure. And so, electric field is kind of like pressure. And instead of talking about actual energy, we talk about energy per charge. Right. Okay, well, let's just do a couple more. And again, we're just trying to get fluent with the vocabulary. Let's take a look at number 12. And it says, what is the speed of a proton whose kinetic energy is 3.2 keVs? Yeah, that's a good one. This is actually kind of like chemistry with doing dimensional analysis. So, kind of, sort of. Okay, so we're talking about number 12. And then we have, I think it's 3.2 keV electron. B equals question mark. So we just introduced the concept of an electron volt, and it's a unit of energy. But this is moving. So this is actually a 3.2 keV electron, means it's got this much energy stored as kinetic energy. So we have two steps to do. We have to get keVs into joules, and then we can solve for velocity, because kinetic energy is equal to 1/2 mv squared. And we do the algebra really quick, so multiply both sides by 2, divide by both sides by m. So that means that the velocity is going to be given by the square root of 2 ke over m. So let's start off by rewriting 3.2 keVs. It's just electron volts. So 3,200 electron volts. And then let's see how the dimensional analysis works for this. Really all we have to do is cancel an electron. One electron has a charge of 1.6 times 10 to the minus 16 coulombs, and a volt times a coulomb is a joule. So that's it. If we just multiply those out, then I'll have joules. So I get 5.12 times 10 to the minus 13. My decimal point's a little bit darker. Right, so that's our conversion factor from electron volts into joules. And now we can go ahead and execute this formula. An electron has a mass That's 9.11 times 10 to the negative 31 kilograms. That in 1 year equals 3.15 times 10 to the 7th seconds. There are all sorts of just random numbers floating around up there. But anyway, let's finish this off. So V equals 2 times 9.11 and this is a, whoops, sorry, I've got my kinetic energy up here. This should be in the denominator. So sorry about that. Decimal point. And then we'll take the square root of the whole thing. So this is a great check for you. We're going to put 5.12. We just want to see how things are coming out on your calculator. It would be great if you could execute this and then just throw a number into the chat so we can see how people are doing. And it makes me feel good too, because it lets me know that there's somebody out there. Anybody, please.
Sorry, is that 10 to the
Minus 13.
the one below?
Negative 31.
Okay, thank you.
Yep, it's tiny. So tiny. And then don't forget to do the square root of the whole thing. It's still a big number. Uh-oh, I'm sorry. Yeah, you know what? Because this is actually supposed to be a proton instead. Uh-oh. If you did it at home, this turns out to be 1.06 times 10 to the 9th power. Yeah. So if you did that, but just, that's faster than the speed of light, and that's not possible. And the reason why I made a mistake is because it's a proton. And so that's 1.7 times 10 to the negative 27. So I'll do this one for you. And then that'll match up. If you're looking at the agenda, there are answers there. 1.67 times 10 to the minus 27. And then we actually get something that makes, that is physically possible. Yeah, no, it's still, well, yeah, no, that works. So 2.448 times 10 to the 6.7. The speed of light is 3 times 10 to the 8, and it's not possible for anything with mass to go faster than that. So that's pretty fast proton. All right. Need new glasses. How we doing? Okay, I don't hear any protesting, so. All right, so 18 is a really nice one to take a look at. And then, yeah, and then 22 is a great one to end on, so that sounds good. All right, well, let's go ahead and take a look at 18. And we go back to talking about potential energy again. Let's get the specifics down. Okay. So the concept about an electric potential for a point charge. We start off by taking a look at tonight we took a look at an electric field established between two parallel plates. And remember, electric potential is code word for volts. For a point charge, we have a different way of figuring things out. The electric potential is equal to KQ over R. And just as a recap, like why do we use capital Q sometimes and a little q sometimes? And the answer is that we use a capital Q because it really affects space around it. And the little q's are usually test charges that don't really cause that big of a splash. So we've got a proton. And then these two protons are close together. So what's the electric potential? And we're only 2.5 times 10 to the minus 15. So that's R. And we're thinking about a proton and the nucleus. So proton to proton distance in the nucleus. So the idea is that we have two positive charges in a nucleus. But in case this one isn't there, and we're just focusing on this particular location, then the electric potential answers the question that if we had a positive charge, how much energy would it take to get it there? So we're looking for V. That's going to be volts. And then we have K, of course. And then the charge is a proton, so that's 1.6 times 10 to the minus 19. And then divided by our distance, which is 2.5 times 10 to the minus 15. This is electric potential. So it's an R, it's not an R squared. R squared is what we have when we're doing our electric field. Electric field is analogous to force, and electric potential is analogous to energy, and that's how come there are two different forms. So let's just try this really quick. Giant exercise in numbers very small and numbers very large. And I get 576,000 volts, which is a kilovolt. And so I'm going to write it like this. This is 576 kilovolts. So again, I'm just trying to show you how this works. This is the electric potential at that particular point. Now, if I have a positive charge and I wanted to walk it in, so here's a little stick figure that's holding onto a positive charge and is trying to walk that in, then it's going to be an uphill climb. And the nice thing about electron volts is that if we're going to try and bring this positive charge in here, is that I can just rewrite this as 576 keV. And that's our energy needed to walk it in. Now, the other really nice thing about talking about potential energy and electric potential is that they're scalar quantities. We don't have to do direction. So you can see why electron volts is really handy energy. We're talking about the voltage due to a single point charge, but then if we were trying to bring two together, because this has the elemental charge, then we just put an E in there and we're done. That's super handy. All right, so just check it in again. Any questions really quick, and then we'll tackle our last one for tonight. Okay. Well, let's take a look at 22. Hopefully you have the agenda open. It says 2-point charges, 3 microcoulombs and -2 are placed 5 centimeters apart on the x-axis. At what points along the axis is A, the electric field 0, and B, the potential 0? Ah, yeah. That thing again. Oh, I love this question. I think it shows up on the quiz for chapter 17, and I think it shows up on one of the exams. So much fun. Okay. So we've got these 2 different charges, and we have a separation between the 2. Right, so 3 and 2.
Just a moment.
I said something to wake Siri up. All right, 2.3 and 2, and 3 plus 2 is 5, of course. And they are 5 centimeters apart. So in our conversation last time, we said, you might as well set up an axis between the 2. And then if we're trying to find out where the force is equal to 0, or the electric field equals 0, same difference. We're going to bring in a positive test charge, and we're going to see if that's a possibility or not. Actually, well, I said red is positive, okay. So positive test charge. And in this region. So it gets repelled by this one and attracted by that one. So that's a possibility. But if they're going to balance out, we need, don't forget, we've got electric field that's equal to K Q over R squared. All right, so if we're going to get the 2 electric fields to cancel each other out, but the charges don't have the same value, then we're going to have to count on the distance to make up the difference. And here, the distance will never make up the difference because it's 1 over R squared. we're too close to the bigger charge. And here it doesn't work because we're going to be electric fields point away from positives and toward negatives. So both the electric fields will point to the right. So only out here do we have a possibility. And so I can call that region X. Actually, I just put a little mark here, and we'll call that X. Right, and then we set the two electric fields together, and we recognize the fact that we purchased a ticket to Quadratic Formula Town, and so we're going to have to do that. Now, potential is equal to KQ over R. So in this case, remember, potential is a scalar. And we don't have to do that whole rationing about which way does the electric field vector point. Instead, what we're trying to think about is that it's simple addition. We need to find a place so that the electric potential from this plus the electric potential from this is equal to 0. So if I picked a point, again, out here, I don't know why I blew that, just up here, right? So the electric potential due to this is going to be positive, and the electric potential due to this is going to be negative. But there's no shot at these equaling out because I'm closer to the bigger number. Okay, so that's not going to work out. And then up here, I'm always closest to the negative number. So this is going to be negative out here. If you remember that plot we did where it spikes, then it goes down here, and it slowly comes back up from the negative region. So it's actually in the middle for our potential. This is where the electric field could equal 0. And this is where V could equal 0. The potential would be equal to 0 somewhere in between the two. Because this is going to be a positive potential everywhere, and this is going to be a negative potential everywhere. And so that's the only shot where there could potentially be 0. So let's go ahead and take a look at how we would figure this out. Let's call this Y, just to make it different. Okay, so I'm going to have K times plus 3 microcoulombs over X plus 5 squared. And then that's going to be equal to K times, we'd use the positive 2 microcoulombs because we've already done the reasoning about the effect of it being negative. And then that's over X squared. So we have lots of cancellation to happen here. So the K's are gone. And the microcoulombs are gone. And we can cross multiply. So this is going to be 3x squared is equal to 2 times the quantity x plus 5 squared. If I was going to do this, I would divide both sides by 2 first. So this would be 1.5 x squared, and then expand this binomial. So x squared plus 10 x plus 25. And then I can whip it into quadratic formula shape and then plug in numbers in. But then let's see what this looks like over here. So this is going to be K times 3 microcoulombs divided by the distance from here to here is y. And then we'll do K and 2 microcoulombs divided by, and then we need this distance. So that's going to be 5 minus y. Once again, lots of cancellation. Microcoulombs are gone. K is gone. And now this is not a quadratic. So you can actually just do the algebra and figure out what that is. So here's the deal. Why don't you go ahead and do the algebra and figure out what y is and pop it up in the chat. And then I'll do the grunt work and plug this into the quadratic formula and see what we get. Okay, and mark, set, go. I call quadratic formula. I'm almost there. You're going to beat me. Probably. Okay, and we got any entries in the chat so far? Yeah. Yes, isn't it nice? We like scalars, yes. So Kendall, check. Beth, check. Hold on. So I'll just bang out the algebra really quick. We're gonna, I guess it's called cross multiply, right? So 3 times 5 minus y, 2y. Wow, so much easier. So this is 15 minus 3y equals 2y. Added to both sides, so 15 is equal to 5y, and that's y equal to 3. And over here, this x turned out to be about 22.
I have a quick question on that.
Yeah.
For the
Looks like my mic dropped out.
oh, can you hear me? Can you hear me?
Okay, yes, Christoph, go ahead.
Okay. So for that one, we're doing the y referring to the 3 microcoulomb charge, and then the 5 minus y referring to the 2 microcoulomb charge.
Yeah, that's right.
How did we decide to do the 2 microcoulomb as the 5 minus y instead of the 3 microcoulomb charge?
Yeah, I mean, that's a totally valid question. Let's see what happens. Right, so the question is, I think I'm understanding it is that what if y was under here and 5 minus y was over here? Right?
Yeah.
Yeah. Yeah, okay, so then this would be 3y. And this would be 2 times the quantity 5 minus y. So that would be 10 minus 2y. And then 3y over here, and then y would be equal to 2. Right?
I would think so, but I
Yeah, yeah. So it just says when we put the y over here, we got 3.
Yeah.
So that means this is 3, and it makes sense because it's actually closer to this one. So when we put it in y here, we get 3 here and 2 here. If we put y in matching up with this, then we get 2 here and 3 there. So it's a good question. There wasn't any, mysterious footnote that led me
Okay.
there.
All right. Thank you.
Yeah. All right, thank you for that. Okay. So that should be, I'll just let people kind of settle in there. All right, any other questions? So quiz for 16 is going to be posted on Canvas, similar to 15. And that'll be due on the weekend at some point. Then as far as practice work, we can still go ahead with the doing the problems that are posted on Canvas. But I think I'm ready to offer up an assignment that would be optional on mastering physics. So we can sort of work our way into it. I don't want to go all or nothing. But yeah, I mean, there are definitely some benefits from using mastering physics, especially the adaptive questioning. So if you get something wrong, then it can come back with something that's more foundational, and then you can move forward. So we'll do it sort of on a trial basis and see how it goes. But I think that's about it for tonight then. So you have enough so we can start moving forward.
I just had a question about that mini lab. When is that due? Due last week.
Honestly, I'm so buried right now, Z, that I would prefer if you didn't submit it right now. But maybe this weekend would be great.
Okay.
Yeah, how about that?
I haven't finished it yet, so that's fine.
Yeah, sounds good.
All right. I think that was it. Thank you.
Yeah, you're welcome. If you want to talk to me in a smaller group, just hang on. But that's it for tonight. Thanks for being here.
Thank you.
Yeah, thank you for coming on as well.
Thank you.
All right. Have a good night.
Appreciate it. Thank you.
Hi, I just had a quick question.
Yeah, no problem.
Where do I find more information on the mini lab?
Yeah, it's on Canvas. So let me share my screen really quick.
Okay. I went down the list in the center part, but I couldn't.
It's this one right here. It says electric fields.
Electric field. Okay, under 16. Thank you.
Yeah, you're welcome. Have a great night.
Right, thanks, you too.
Okay, bye-bye.